Greetings everybody, and welcome to the HEXRD tutorials. Today we are going to be discussing the FIDDLE workflow. FIDDLE is a time-resolved X-ray diffraction diagnostic at NIF, the National Ignition Facility. And within HEXRD and the corresponding GUI application, HEXRDGUI, we have designed a full workflow for importing the data, calibrating, and analyzing lineouts. So, to start, we're going to assume that you've already collected your FIDDLE data sets, and once you open up the HEXRDGUI application, you begin by clicking File, going to Import, and clicking LLNL Import Tool. So this is an import tool for the various instruments at Lawrence Livermore, and we're going to select FIDDLE from this drop-down list. Okay, so you have a few options after you select FIDDLE. If you have image plate data that you want to include and visualize, you can select with image plate. Otherwise, select without image plate. We're going to keep the image plate for this tutorial. You can also select a starting instrument configuration that you'd like to use, or as we would often do with FIDDLE, is load atlas coordinates, which gets our instrument in a very close state to the correct answer, off by only a couple millimeters or so. So in this case, I'm going to click to load the atlas coordinates, and I have them in this directory right here, atlas APH. So you can see I have those loaded, and the instrument will be using those. Now we're going to import the images. And there's 5 cameras for FIDDLE. Currently we have it set up so that if all of the files are within the same directory, HEXRD can automatically identify and pair the different types of files, including image files and dark files. So that's what we recommend. When you click Select Image, you can see I have all the files right here. The data files end with 999, and you can see this one's for camera 2, this one's for camera 3, etc. The dark files end with a different number, and in this case it ends with 3. So just selecting one of them, HEXRD will automatically identify and pair up all the camera images using that notation. You can look at them and verify that they're correct. For camera 2, it's using these file names here. For camera 3, which you can look at the data for them by switching them here, it's using these file names. And now we're going to load the image plate. So as I mentioned, we used with image plate earlier, so we're able to load one here. The image plate file contains image plate in its name, so it's that last file right here. Now when you load the image plate, because the image plate was scanned from a detector film, you have to perform a cropping step to crop out the actual image data. And we have these templates that you can use in order to do that. So this template will appear. You drag it to align the squares with those white spaces, and the outline as well. And once it looks good, you can do other things, by the way, to help you. For example, you can rotate as well if you need to, or just completely transform the image, like mirroring it or rotating it. But once it looks good, click Save Image Plate Boundary, and then that template is saved. Afterwards, we've done everything that we actually need in the import tool. We're just going to click Complete and Reload Instrument. Now for FIDDLE, when you do this, not only does it reload the instrument automatically, but because the data is somewhat noisy, people would often apply a median filter. So it pops up a median filter option. where you can select the kernel size. We're going to leave it as default. It does take a little bit of time to run the median filter. After it finishes, the physics package manager appears, where you will set up, input different settings for your physics package. In this case, the sample, for this example that I'm showing here, the sample is Syria. So we're going to select Syria, and the thickness is 35 microns. You'll want to select the correct options for all of your different layers that you have. In this case, we're only going to have a sample, a window, and a pinhole. So for the window, it is already set up properly. It's LIF, and the thickness is 150 microns. For the pinhole, the material is molybdenum. You can select it from the list here. And the thickness is 100 microns. The diameter is 400 microns. So those are all correct. Once you have all of those options set up properly, just click OK. We'll be using those options later in order to perform corrections for the diffraction patterns that appeared for from the different layers. So the initial view here is a raw image view. We're going to perform a couple of quick image corrections. Subtracting minimum usually helps a little bit. More importantly, we're going to apply a pixel solid angle correction as well. And once that's applied, you can see some of the diffraction lines from the images. When I click that B and C up here, that brings up the brightness and contrast editor. Because these images have such different value ranges, you can see a histogram here. This is actually for the image plate. Most of the image plate values are much lower than the camera values. And because there's a very different distribution of values in the different images, it's hard to visualize them all simultaneously. But you can do other things like start up this tabbed view, which takes a second to generate because of most of the things that are running slower because of the median filter. It redoes it. And you can look at the images individually if you so desire. This one is the image plate. I'm going to switch over to the Cartesian view now. Oh, by the way, you can select time steps at the bottom here as well. For FIDDLE, there are 4 time steps, each one occurring over a 2 nanosecond window, I believe. And here I'm going to reduce the resolution of the Cartesian view so it renders faster. So this is a low resolution form. But you can see if I click on this arrow here, it switches the frame. Actually, it takes a second to load the data, mainly because of the median. And then the value ranges are different too, but you get the idea. Okay, I'm actually going to remove the image plate because it helps us visualize the ranges of the data a little bit better with it being removed. We're also going to want to remove the image plate later anyways because it doesn't contain any data that we're going to use for our calibration. So often once you get to the calibration step, you would want to remove it. The way you remove it is by selecting it from this detector parameters list and clicking remove detector. And let me rescale these colors here, the color ranges. You can also hide the detector borders if you click on this here. And I'm going to increase the resolution of the Cartesian view here. So now you can actually see lines on all of the different cameras. And what we're going to do now is we're going to project the simulated diffraction patterns on top of it to see how well they line up. So to do so, we already have a Syria material here in our materials list, but we're going to want to import molybdenum as well, because some of the lines are from the molybdenum pinhole. And then we're going to go to the overlay manager. We'll add the Syria lines. And one thing that's important for us to do is to take into account the correction due to the physics package and the pinhole. So for Syria, because it's the sample layer, we would want to select the layer correction type and the sample for the layer type. Also, I'm going to only select the HKLs that intersect with the cameras, where we can actually see their data. Some of these other HKLs which don't intersect with the cameras, we can just ignore those. I have those written down here. So those are the ones that intersect with the cameras. All right, now I'm going to add a molybdenum overlay as well. This one I'm going to change the style immediately to include red, so that you can easily distinguish between the molybdenum and the Syria simulated diffraction patterns. And we're going to also do a pinhole camera correction, but this time it's a pinhole correction. And we're using Ryan Riggs' formula for that. Also, I'm only going to select these two HKLs, since those are the only ones for molybdenum where we see the data. Now if I hide and show the overlays here, you can see that they actually line up already fairly well with the data, at least within a few millimeters. They're off a little bit, as you can see, but we're going to correct that in the calibration later. But you can see in the data that this line right here is caused by the molybdenum pinhole, and the other lines are caused by the Syria sample. Now we're going to head over to the polar view. This is the one that you will probably work in the most. There's a bunch of white space around the camera images here. So one thing I'm going to do is reduce the eta and 2 theta ranges so that they're more closely wrapped around the actual data. I'm going to reduce the eta range to -60 to 170 and adjust the 2 theta range to be 22 to 72. I'm also going to increase the pixel size a little bit. Sorry, decrease the pixel size, which increases the resolution. It makes for a smoother line out at the bottom, and it makes the data appear smoother as well. We're also going to apply a snip background correction. You can see that when I apply one, it reduces the background and the line out below significantly. We're going to do snip 1D. And we're also going to apply erosion. I'll actually rescale these colors so you can see what that did. The erosion just erodes some of the edges of the detector. So you can see that the lineout background below is a lot smaller. There are some extra peaks here caused by artifacts from the SNP algorithm. And what we're going to do with those is mask them out. So I can go to Edit, Masks, Draw, Polygon, and I can click around them, right click to start a new mask. You can see the dots are a different color. We're going to be masking out these SNP artifact regions. I'll do it relatively quickly. If you want to do it with more precision on your actual data, you can feel free to do so. And then click OK. So that masked out the SNP artifacts, and you can see that it eliminated some of those artificial peaks in the line out below. I'm going to make the simulated overlays appear again here. You can actually already see from the line out below, you can kind of already see which peak belongs to which material. Like you can see that the molybdenum simulated peak here is close to this one, and the Syria is close to this one. So when we calibrate, they're going to line up a lot better. And interestingly, you can also note that because of the different corrections, you can see that the lines up here for molybdenum, for instance, are not perfectly straight because they take into account the pinhole corrections. If you want them to appear straight in the polar view, you can actually distort the whole polar view according to that correction. And in this case, I distorted it according to the Syria sample layer correction. That makes the Syria lines perfectly straight. If I switch it to the molybdenum powder, it's going to make the molybdenum lines perfectly straight. So we'll leave it like that. Alright, next we're going to do calibration. So what we're going to do is we're going to click Run, Calibration, and perform the composite one, which you can do calibration using Laue as well with this one. But in this case, we just have two different materials with powder lines. So you can handpick. You can go through and handpick these. I'm going to reduce this zoom box a little bit. And this line, we don't actually see data for it because it was on the border. So I'm just going to right click to skip it. This line that's now highlighted here, that's HKL220 for Syria powder. We're going to left click and then you just go through and you select some points. And you want to be pretty accurate with your point selection, as accurate as you can be, because the calibration will be based upon that. The calibration will be getting the simulated lines to match up with the points that you selected as much as possible. So I'm not going to go through and do all of them. Instead, I already have some points I picked earlier that I'm going to load through for the sake of time in this video. So for Syria powder, I'm going to load these picks. You can see if I zoom in here, the picks that were made before for each of the lines. You just do them to the best of your ability. Click OK. And then for the molybdenum powder, I'm also going to load the picks. You can see those here. These are molybdenum picks up here. And in this view, you can click on them to highlight points, and it highlights the overlay that it corresponds to, things like that. Okay, now the calibration dialog appears, and this allows you to choose which parameters to refine in order to get the simulated overlays to align with the points as much as possible. Some important things for FIDDLE are that you should make sure that this relative constraints here is set to instrument rigid body. That's because the detector's relative positions to one another and their relative tilts with respect to one another should be already very accurate to a high precision. So you don't want to allow detectors to move individually. You want to make sure that they all move as a group because of the way that the experiment is set up. And then likewise, for the tilt center of rotation, you want to make sure that if you're modifying tilt parameters, that the center of rotation here is set to origin, because the experiment necessitates that if there's any tilt in the detectors, that means they must have rotated about the origin. So these are the necessitated settings for this type of experiment. You also probably do not want to click this reset relative params to 0 button unless you really intend to do so, because oftentimes it's very important for you to record these values that come out, the relative translations and tilts, and resetting them to 0 would make you lose that information. Okay, so the only things we're going to actually calibrate for this example are the whole instrument translation vectors, so the x, y, z for the whole instrument. This will move all of the detectors the exact same amount in all directions. And we also will refine the beam vector, because there's some uncertainty in the beam vector as well. So I'm going to turn off the tilt parameters, only refine the translations. You can see you can set some delta boundaries over here too. And I'm going to click Run to perform the first calibration. You can see as it runs, it prints out information about each iteration, and you could actually see the cost function being reduced. You can see the new parameter values here. So the translation, the x shifted by 0.3 millimeters, I believe, y by 1, and z by negative 0.432. You can also see those numbers over here in the calibration results. And you can see that the picks align much better already with the simulated overlays here. What we're going to do next, calibrating can be an art. It's important usually to calibrate the thing that needs to change the most first. But now that we've calibrated the translation, we're going to switch over to calibrating just the beam vector. This should reduce the cost by a little bit. And they did change. This rounds the numbers in the display here, but the numbers did change a little bit, and it did reduce our cost by a little bit. You can see that by zooming up here. You can see the cost was reduced. That's this number. And then finally, we're going to refine all of them together. The delta ended up changing to 0 for this one, because the delta actually decreases when it refines in order to prevent the value from wandering too far away from the initial conditions. So it originally had a value of 0 and a delta of 1. Because it went all the way up to 1, the delta changed to 0, so that when you run it again in a subsequent run, like now, it wouldn't go beyond that boundary that you had set earlier. In this case, we want to allow it to move again, and I know it's actually going to decrease because I've done this before, but I'm going to increase the delta value here so that it can shift again. So we're going to refine all of these together now, the beam vector angles and the translation vectors. You can see the cost dropping again. And here's the result. You can see that the simulated data much better aligns with the peaks now. We could keep on going, we could refine things further, but I'm going to leave it as is for now. So this could be one of the things that you would need to record after you finish the calibration. These numbers, how much distance off the instrument translation vector was, or the tilts if you refine the tilts as well. So make sure you record these numbers. If you want to record them after you close the dialog, one thing you can do is go to the instrument settings in the slider view here, and if you click this lock relative transformations checkbox, then these values in the translation and tilt sections are identical to the ones in the calibration. So you can see those here, and you can actually modify them here too if you want to try to interactively and manually align the data. You would want to also here select the center of rotation to be origin, by the way, if you modified the tilt parameters. Okay, so let me see here. I have one more thing I'm going to show, and that's the waterfall plot. After you have calibrated your data properly, one thing that you can visualize is all of the different frames together, the lineouts for them. And that can be done by clicking this waterfall plot button. So I'm going to click it. It's going to generate the azimuthal lineouts for each frame, and then they appear here in this waterfall plot. Now these are all adjustable. You can see the frame numbers in the legend here. You can left click them and drag them to move them closer together. You can use your mouse wheel to rescale them if you're just looking for features. You can actually move them left and right as well if you follow these directions up here by shift clicking, although that would make the bottom x-axis 2 theta values incorrect for that one, the one that shifted left and right. But you can see the different features and how they change over time, because these represent different time steps. This would be the first time step, and this would be the last one. In this case, there shouldn't have been any change really, so the differences here just due to noise in the X-ray and in the timings and things like that. But for real data, you would be able to see different peaks forming caused by the changes during the time steps. All right, that concludes the FIDDLE tutorial. I hope you enjoyed it, and feel free to ask us any questions if you are running this yourself. Thank you.